Polynomial functions are functions in this following form: an times x to the n plus an minus 1 times x to the n minus 1 plus an minus 2 times x to the n minus 2, and so on until we get to a1 x to the first plus a0. I guess this is a kind of low. So x to the first. And a to the 0 is the same as a to the 0, x to the 0, but x raised to the 0 power is 1, so we just write a to the 0. And the first thing to talk about really is what n is. And n is the degree of a function, and the degree is the largest power of x. So if I have some equation, let's just say x to the 8th minus 7x to the 7th plus 3x to the 4th plus x third, minus 4. And I want to know what the degree is. We just have to look at which power is the largest, and here it's easy to see that it's 8. So the degree of this polynomial would be 8. And all this is doing here is just setting a standard form for polynomials, for any polynomial, because we can have a function with a degree of 10, we can have a function with a degree of 4, we can have a function with a degree of 100. So what this is saying is we put in our largest degree, so let's say here it's 8, so a to the an, which would just be a8, and all these a's are just the coefficient. So here our coefficient is 1, so if we put in 8, so a8 would be 1, and then we would go on to our next coefficient and power. So this would be 8 minus 1, so it would be a7. So a7 is just the coefficient of the x to the 7th power, and that would be minus 7, and so on until we get to a0, which is here 4, or minus 4. So this is just a standard form for polynomials, and we've been dealing with polynomials already. Polynomials include quadratic functions. A quadratic function is a polynomial with a degree of 2, so n is equal to 2. So if we were to put n is equal to 2 into our equation over here, we'd get a2 x to the second plus an to 2 minus 1 is 1, so it's a1, 2 minus 1, that's x to the first, and then we get a to 0. And this is just another way to write the standard form of a quadratic equation. We usually write it as ax squared plus bx plus c. And all we've really done is replace a2 with a, a1 with b, and a0 with c. Otherwise it's the exact same thing. And all this is doing is just writing a standard form for different powers. And there's only one more thing to mention about polynomials. Polynomials only include integer powers, so n must be equal to a positive integer. So numbers like 1, 2, 3, 4, 5, these are all good. Numbers like minus 1, a half, 3/4, 5/4, minus 2, these are all bad. Well, not really bad, they're just different from polynomials. These aren't polynomials, and the reason we don't include them in polynomials is because these ones have issues with domain, with a, obviously x, well, let's talk about it. So x to the 1/2, this is the same as the square root of x, and here we can't have negative numbers because then we get an imaginary number, and we don't want that. And the reason we don't include negative powers like this is the same as 1 over x squared. And again, we have a problem where we can get a 0 in the denominator. Polynomials, their domain is all real numbers, and the range just depends on whether it's an even or odd function. So actually, now that we are talking about range, let's talk about the properties of polynomials. Polynomials really, the only term we really care about is the term with the largest degrees. The only one we really care about is x to the 8th in this problem. And the reason is because x to the 8th is going to tell us, the highest degree of a polynomial is going to tell us what the overall behavior is going to be similar to. So here we have an x to the 8th function, and this is going to act very much like, so this whole thing is going to act very similar to x to the 8th, assuming that x goes to infinity. Obviously, when we're dealing with smaller numbers, it's going to be a little bit different. So actually, let's go on further with this. It's going to act like x to the 8th, which is an even function, which means it's going to look like x squared or have similar properties to it. Its domain, its graph is going to look somewhat like this. Now, it won't look exactly like this because we have all of these other terms in there. So what it might end up looking like is it might look something like this, where there'll be like a few squiggles or a few bumps in it. But over the long run, we can see that it still has this general U shape, like this. It has the two ends pointing up, and although there are these few bumps right here, it still has this sort of U shape to it. And if we were to have a function, let's say, that was x to the 7th plus some other stuff, this would act like x to the 7th, which is an odd function. And therefore, it would act similar to x to the 3rd. So that would have a graph that would look somewhat like this. Now again, in the middle, depending on what is being added and subtracted to it, it may look very similar to this. It also may have a few bumps, like the other one, like this. But it would still have this general half parabola shapes on opposite sides. And we'll talk about the reason why it is. But this is really just a review of our properties that we learned earlier, where we know that x to the 6th, x to the 4th, x squared, they're all even functions and they all behave in a similar manner. And same thing with odd functions, x to the 5th, x to the 3rd, x to the 9th. These all behave the same way. They all have the same domain, the same sort of range. And a lot of people might be skeptical because they can see that if we have, let's take a different example. I guess the easiest way to explain this is to make a table. So let's say we have this equation, x to the 4th minus 10x cubed. Some people might be confused in how this graph would look like, because obviously we have an x to the 3rd function and it's subtracting x to the 4th, and x to the 3rd looks like this, and x to the 4th looks like this. So what exactly happens? Do they sort of fuse together and have some kind of weird thing that looks like this or something? No, actually, like I said, the only term that we're really going to care about is x to the 4th, because it's going to overpower x to the 3rd. And that's really, well, let's make a table. It'll all become clear when we make a table on why the highest degree one is so important and the other terms are sort of irrelevant in the big picture, the smaller terms, smaller degrees are basically irrelevant. So let's start. Let's make a table. We have x to the fourth, and I'll put the minus side out in the middle here, and 10x cubed. So let's just start putting in numbers. Let's say we have 1. So right now we have 1 times 1 times 1 times 1 times 1. And over here we'd have 10 times 1 times 1 times 1. So we can see right now that this term is greater than this one. So the graph should have more x to the third character, because this one is so much larger than this one right now that this number is not going to have much of an effect on this one for now. But as we get larger, we'll just do 2 for now. You can still see that this is much bigger than this number. So we have 2 times 2 times 2, and this is 2 times 2 times 2 times 2, but this one has a 10 instead of a 2, so this is going to be quite a few times bigger. So let's continue on. We have 3, and here we also have our 3's. So here we have 3 times 3 times 3, 3 times 3 times 3, but here we have a 10 instead of a 3, so this one's going to be larger. And this is going to continue. This term is still going to be dominating until we get to 10. So we have 10 times 10 times 10 times 10. And here we have 10 times 10 times 10 times 10. And at this point, they would be equal to each other. So from 1 until, let's assume that we start at 0. Well, we don't include 0, because then the whole thing would be 0. But let's just talk about the positive numbers. From 1 all the way until 10, this term has been greater than this one. But now, once we pass 10, that's going to change. So here we have 11 times 11 times 11 times 11. And over on this side, we'd still have 10, and then times 11 times 11 times 11. So now we can see that this term has finally won. And it's not a lot bigger right now. It's only multiplying it by an 11 instead of 1. But as we get larger, it's not only has it won, but it's going to get larger and larger and larger, and it's going to basically make this term become irrelevant. So let's try 100. So 100 times 100 times 100 times 100. On this side we have 10 times 100 times 100 times 100. So now we have all the terms are the same except for that 10 still. But here we have 100 instead of 10, so this is going to be 10 times larger than this one. And I guess a tenth, because this would be 1/10 of this one, and this is subtracting. A tenth is still a pretty significant amount for most people. If someone were to take a tenth of your money, you would probably notice. But this is only at 100. If we increase even more, we go to 1,000. And here we'd have 10 times 1,000 times 1,000 times, that's 100, times 1,000. Here we have the thousands that are the same, and here we have a 10 instead of 1,000. So this would be 100 times larger now. And now it's getting pretty big. But it doesn't have to stop there, obviously. Let's take it out to an extreme. Let's suppose, well, I'm not going to write this out, but let's suppose we have x is equal to 10 billion. So if I have x to the fourth and 10x cubed, this would be a billion times a billion, or 10 billion times 10 billion times 10 billion times 10 billion. And over here it'd be 10 billion times 10 billion times 10 billion times 10. So this would be a billion times larger. So this is a billion times larger than this one. This one is only 1/billionth of this. So when they're being subtracted, it's taking away 1/billionth of this number. So if we were to put this into perspective on a graph, let's say I wanted to graph our equation, and then right next to it I put just x to the fourth. So at x is equal to 10 billion, what would the difference between these two be? Well, the only difference between this and this is that we're subtracting this 10x cubed. But as we saw here, 10x cubed is only 1/billionth of this number. So if we were to put this on a graph, so if this was on a graph, our point, let's say our x to the fourth point was right here. Our x to the fourth minus 10x cubed would only be 1/billionth below right here. A billionth of it. Obviously, with large numbers, it would be a large numerical value, but comparatively, it's a very small amount. That would be like, let's say that this was, let's say x to the fourth is a person, and they're a billionaire. That would make person 2 over here a billionaire minus $1. That is the amount of difference between this function and this function. So we can see that this x to the fourth term has completely taken over the function, the direction of the function, the direction of the way the numbers are heading, and it's basically made this 10x to the third completely irrelevant. And it wouldn't help if there were other terms like x. And it wouldn't have really helped if there was other terms. Let's say if there was some x squared term and some x to the first and some constant. Now these would be even less relevant than this. So we can see that as x heads to infinity, as x gets larger and larger, the smaller terms become less and less important. When x is a small number, then these values have more pull. As we saw over here, when x is 1, x is 2, x is 3, then these numbers, then this term had more value. But we can see that very quickly at x is equal to 100, it's only 1/10 of what it is. And this is being multiplied by 10. If this had no coefficient already, literally on number, as soon as it was greater than 1, x to the fourth would already be in control. And that's why we get bumps in these graphs. So let's say we had a graph of our function. It would have this U shape, but there might be some bumps. No, that's not it. There might be some bumps in it like that. And where those bumps come from is these other smaller terms. That's them fighting for control of the graph of the function, essentially. But what happens is that as we go towards infinity in the negative direction and the positive direction, they become less and less relevant, and x to the fourth takes over, or whatever the highest degree is. And it doesn't matter how many smaller terms are being subtracted for it, over the long run they become basically irrelevant.